friggin laser beams is something we haven't covered yet. And while there are plenty of tutorials on rendering one single straight laser beam, I haven't seen any about lasers that can reflect and refract off surfaces. So this is what I want to focus on. This video right here will be just about reflecting and refracting. If you want to render laser beams as well, we have another short video where I quickly build the rest of this setup. Also, this video is brought to you by our patrons. More on that at the end of this video. Now, let's get going. First of all, before we dive in, I think I can't start this video without showing the main reference, the main inspiration for the teaser image. And this is the Island of Glass music video made by Polynoid.tv, which is an insanely cool video. So please check this out as well if you want just a really cool example of laser beams in a motion graphics piece. But now let's jump into our Houdini scene right here, which is not an empty scene, and you can download the file that you see here with all the other files in the scene file download. To quickly walk you through this scene, we have a little optical table in here, which consists of a base grid and some mirrors to reflect our laser beam itself, or at least the laser that emits our laser beam, and then also a rotating prism in the middle, which should refract our laser beam. This is our entire scene. For now, I want to get rid of our main base in here, because this just makes everything a bit easier to see. And to quickly walk through the attributes that we have in here, we have, of course, a P attribute. We also have a name attribute, which I simply use for assigning different materials, different parts within Karma. I also have normals, and normals are needed to correctly reflect and refract our laser beam later. And of course, I also have UVs, which again are useful for shading in Karma later. And then the only other thing that we need for a setup are two prim groups. One that stores all the faces that should reflect our laser beam, and one that stores all the faces that should refract our laser beam. So a prism in the middle. And our laser beam itself is just one single point right here at the mouth of our laser with one attribute, a normal attribute, which is the direction that our laser should shoot in. And with this prep done, what we can do is drop down one single point wrangle, and this is the only node that we're going to use in this tutorial, and everything else will happen in here. That sounds super scary. However, what we're mainly going to use in here and what this setup mainly relies on are just three main vex functions. And I think if you have an idea what these three functions do and how to use them, you pretty much should get the gist of the entire thing that we're going to build in here. So let's take a look at our vex functions. First of all, we need to be able to shoot our laser beam into our scene and to see if it intersects with some surface that, for example, can stop our laser beam or reflect it or refract it. And we can do this with the intersect function. And the intersect function takes as inputs, first of all, a position, so the position of our single point in space, and a direction, so our normal for this point. And if the ray happens to hit some other object, some other face, we're first of all going to get the prim number of that face, also the hit position in 3D space where we hit that face, but also the hit position encoded in some other way, the hit position encoded in prim UV space. So think of this as like a little coordinate system for every single face, and the position of our hit stored in this coordinate system right here. If you want to know more about this in particular, you can watch our Kumiko tutorial. However, for now, this is all you need to know. And then, since we want to refract our laser beam in our scene, we need some functions for this as well. And luckily for us, Vex has already these functions pre-built for us. They both take as inputs an incoming direction, the same as our intersect function, and then also the normal of the surface that we're hitting, and it creates a new direction, a direction that's the same as the reflected ray. And the same holds true for refract as well. This also just takes the index of refraction for that surface as well, which makes sense for refraction. And you can think of switching between this function right here and our intersect function. If you run these two functions over and over and over, you can sort of imagine that this means bouncing a laser beam around in our scene. Now there's only one thing missing from our setup, because while we have our direction and we also have our position to shoot our next beam from, what's currently missing is the normal that we need for our reflect and refract function. And luckily for us, there's one additional function that we can use to get this normal. and this is the PrimUV function. But the PrimUV function is designed to work with a primitive number and a PrimUV coordinate. So these two things that we get from our intersect function. And what we can do is we can specify an attribute that we want to sample, for example, a normal vector. And what this will do is it will take a look at all the normal vectors at the corner points for our primitive and sort of interpolate it to another value based on this PrimUV position in our primitive right here. So taking the data from our intersect function, plugging them in here, we should get an accurate normal in here that we can use with reflect and refract. So this is all we need to know in here. And now let's make use of this in our angle. Let's make some room in here, something like this, and let's zoom out in our scene like this, and let's work on our angle in here. Now, first of all, I want to save out some variables that we're going to need for our intersect function and for our reflect and refract functions, and also for, in the end, drawing polylines that will be our laser beam in the end as geometry. So this will be our vector, the position where we're going to shoot our ray from. For our first direction, for our first part of a laser beam, this should simply be V at P, so the position of our starting point. Then we also need our ray direction, so let's call this ray D, and this is, of course, currently our normal. However, our normal by default has only a length of 1, and this may still hit our prism in here, but this maybe won't hit other objects in our scene that are farther away. So I want to make this normal a bit bigger. Let's simply multiply it by a big value, maybe a value of 10. And then finally, I also want to save the current point right here, because later we can use this point to again draw a line to a new hit position. Let's call this last PT. Let's initialize this to add PT num. Now with this all set, we can do our first intersect. So it's right intersect right here. And this takes as inputs, first of all, our geostream. Let's make this geostream 1 because this is where our scene is. Then the position from where we want to shoot our ray. So ray P, then the direction, so ray D, and then we can work on the outputs of this function. Now again, the outputs are the primitive number, the hit position, and the hit position in UV space. The first one, the primitive, is pretty simple. We can simply write in prim and set it equal to the output of a function in here. However, the position and the position in UV space are a bit different. To use these, we first of all have to start by defining some empty attributes to store these results. So let's create two empty vector attributes called hit P and hit UV like this. And let's plug them in as additional arguments into our intersect function. So hit P and hit UV like this. And what the intersect function will do is it will just fill those variables with values that we can use later. Now with this build, we should already get an intersection sort of right here where we are going to hit our prism. And let's test this by simply creating a new point at that position. So int pt is equal to add point. And this takes as a first argument a geostream. So let's put in 0 because this is where our laser beam lives. And then the hit position that we found with our intersect function. So hit p. Let's test this out. And indeed, we have another point now right here where we're going to hit our prism. Let's also draw our first part of our laser beam by adding a primitive as well. So add prim, and on geostream 0 I want to create a polyline, and that polyline should go from our last PT, so this point right here, to our new PT, so just PT, this point right here. And now we have the first part of our laser beam. Now once we had a surface, we need to reflect or refract into that surface. Let's maybe cover the refraction first. And for this, we also need the normal of the surface that we hit. And again, for our normal, we're going to use our PrimUV function. Let's create another vector variable. Let's call it hit n, hit normal. And again, we're going to use a PrimUV function. And we're again going to need a geostream. Again, geostream 1 for our scene. And then the name of the attribute that we want to grab, in this case n for our normal. And then the values from our intersect function. So prim for our primitive that we hit, and hit UV for the hit position in UV space, like this. And let's quickly test this out if that works by setting our hit n as a normal on this point right here. So for this, let's use a setPoint attribute function, and this has loads of inputs. So this is going to be geostream 0, an attribute called n, so we can visualize it on a point t, a value of hit n, and we want to set this like this. And yes, this does look like our normal. So this is looking fine. Now with our normal calculated, we can refract our laser beam. And for the refraction, as we're outputting a new direction, I want to update this ray D right here. Let's say ray D equals our refract function. Now this takes as input our current ray, our current ray direction, and our normal, so hidden, and then also the index of refraction. And let's just pick 1.5 for now. And let's see if that works. And let's simply, instead of hidden, write ray d in here to get the refracted ray direction. And let's take a look at this. And this is not looking correctly because it's simply continuing in the same direction as before. So what's the culprit right here? Well, the culprit here is that this ray d input right here should have a length of 1 to work correctly. However, currently it has a length of 10 because this is what we multiplied our normal vector in here by. So to again make it a length of 1, let's normalize it. So normalize ray d like this. And now this is looking like it's refracting correctly. And also, since this is a current ray direction and our ray direction should always have a length of 10, so we can hit also the more distant objects in our scene, let's take the output from this, which by default is a length of 1, and again multiply it by 10 like we did up here. And now this is actually the main part of our logic in here done. What we need to do now is to do this over and over and over again to make a laser beam bounce around in our scene. So to do this, we need to wrap all of this in a for loop. But what I want to do first is I want to sort of prep the next iteration of the for loop. And for the next iteration, we need a new and updated ray position, a new and updated ray direction, and also a new and updated last PT to again draw a line. Let's do that next. Let's first of all get rid of the set point attribute in here. We don't need that anymore. And down here, let's first of all update our attributes. So our new ray position will be the last hit position. So basically this point right here. Our new ray direction is something that we've already calculated with our refract function. So we don't need to change anything in here. And the new last PT should be the point that we created in here. So PT like this. And with this done, we can start with our for loop. So below where we initialized our values and above where we do all our calculations, let's write a for loop. For I starts at 0 and I like this. I is smaller than how many times we want to have our ray bounce around in our scene. Let's maybe also pick 10 in here. And I plus plus. We want to do all the stuff that we built in here. Let's encase it in curly brackets and let's indent it. And if we take a look at our output now, this is looking a lot more correct. And if we scrub around in our timeline, this is also already looking like a laser beam, at least refracting in our scene. However, we have a couple of problems, and we see one of them if we jump to frame 1 and take a look at this mirror right here. So we have two problems. First of all, this is not acting like a mirror. It is not reflecting our ray. It's acting like a piece of glass and refracting our ray. This is something we need to fix. However, what we also need to fix is that our ray beam simply ends here. And the reason it ends here and does not continue traveling past this pane of glass is we only built one case in here, and that case is where we do actually hit a primitive. If we don't hit any primitive, then our code does not know what to do, and it simply ends in here. So this is something that we need to fix. Now, luckily, fixing this is pretty easy. After we've done our intersection in here, we can simply check if we actually hit a primitive, because if we don't hit a primitive, this number right here that's output by our function will be -1. So let's do a check. If prim double equals -1, what we want to do then is just pick a point somewhere deep in space, somewhere deep in our scene where we don't see it anymore, and simply draw a line to this point. And this is fairly easy to implement. What we need to do is we need to grab these two lines of vex where we create our next polyline and just copy this inside our if statement like this. And for a new point that we are creating in here, what we don't want to do is put it in the hit position because we don't have a hit position. We simply want to put it into our current ray position and add it to that the current ray direction. So since this is our ray position and our ray direction goes somewhere out in space, our point will be somewhere out in space as well. And then finally, once we have done that, we can simply break out of this entire loop and simply stop shooting rays into our scene. Now our laser is somewhere in space where it does not matter anymore. And again, we can just stop doing our code. And yeah, this now looks a lot more correct. And if we run through our timeline, yeah, this also looks a lot more correct now. So one problem down. The next problem is that currently everything is refracting a laser beam and not, for example, reflecting. And there's even a third case, for example, once a laser beam hits this laser source right here, because this is just, I don't know, some black plastic. This won't reflect or refract a laser beam. This will just stop a laser beam. So this is something that we have to check next. Again, the thing that I use for checking this are some prim groups. We have a reflect group and a refract group. And if the primitive that we hit is in the refract group, we want to refract it. If it's in the reflect group, we want to reflect it. And if it's not in both of these groups, we simply want to stop our laser beam. Let's implement that next. To do so, let's take our refract line of code in here and wrap this in an if statement as well. So if something happens, then we want to refract our array. And the thing that we want to happen, or the thing that we want to check, is if the primitive is inside that specific prim group. We can check this with an inPrimGroup function. And this again, first of all, takes the geostream1 for RC, then the name of the group, in our case refract, and then finally the prim that we hit. So again, prim. Then let's simply tag on the next case, so else if. In this case, we want to check if our primitive is in the reflect group. So let's just copy all of this in here and change it to reflect. And the thing that we want to do in here is basically the same as we did with our refractions. We just want to use, again, the reflect function instead of the refract function. And for the reflect function, we also don't need the index of refraction. So just get rid of it. And everything else can stay the same. So now we have our refraction covered, we have our reflection covered, and this is also something that we can already see in our viewport. The last thing that we want to cover is if we hit something like here, like a laser, that will stop our laser beam, and this will simply be one last else. And the one thing that we'll do in our else in here is again stop our reflection and refraction loop, so just break out of this loop like this. And the laser beam right here is stopping somewhat early, so let's maybe turn up the number of reflections and refractions. Let's maybe go to 100, and yeah, this is looking a bit more proper now. Now at this point we are pretty much done with our code. So this is all that we need to write in here. However, there's one tiny bug in here that we still need to fix. And the tiny bug gets a lot more visible if we set our number of reflections down to 2, just 2. And if we now play the timeline, we can see our laser is sort of stuttering. It's stuttering sort of in and out of existence. So what is happening here? Well, we can get a feeling for this if we take a look at the prim numbers, because we have one prim number right here for our first part of a laser beam, but then also hidden in here another prim number. And I hope you can see this. And what this means is that in here we don't have 1 point, we have 2 points, and we have one very, very tiny polyline in between them. And the reason for this is with this intersect function, there's a slight chance that we're going to hit the same face 2 times. First hit and then the second hit as well, because our point, our hit point, is just slightly above the plane right here. So what we need to do is we need to build in a bit of tolerance. We need to take our array position and just move it slightly inwards so that we're definitely below the face that we hit in our last iteration. And this is something that we can do fairly simply. For this, we are going to get another vector, a vector that we're going to call tol for tolerance. And our tolerance vector should point into the same direction as our ray D, our ray direction, but it just should be very, very tiny, very, very short. And we can do that by simply taking the normalized value of our ray direction, ray D, and just multiplying it or scaling it with a very small value, so maybe 0.001. And then in our intersect function, we're just going to take our tolerance and just add it to our ray position, like this, to just move our ray position again a tiny bit inward. And once we do that and play our timeline, now we don't get this flickering and our refractions are looking great now. And now we can go back to the beginning of a for loop, again turn this up to 100, zoom out of our scene and let's play this, and yes, this is looking like a proper laser beam. And this is also all I want to do in this episode. Again, if you want to know how I shaded this and rendered this, there's another short episode that you can watch as well. But until next time, it's cheers and goodbye. And if you like us and want to support us and keep videos like this coming, please consider becoming a patron of ours as well. Again, you're going to finance videos like this, but you're also going to get 2 bonus episodes each month and also instant access to all the bonus episodes that we created since, I guess, about 10 years now. So again, a bunch of stuff is waiting for you there. Also, a ton of thanks going out to all our existing patrons. Without you, this channel would not be possible. Thank you.